So in this video, we're going to introduce the topic of torque. And so let's think about this. Suppose we had a wrench and we're trying to turn this bolt, which is stuck. So if we applied the same amount of force, so force 1 equals 2 and 3, at 3 different locations along the wrench, which of these forces would have more of an impact on actually turning the wrench? So think about that. And you should know from experience that force 1 is going to produce the biggest impact, and that's because it has mechanical advantage. Which you should have, or you probably learned about in middle school, because it's a lever. And a lever's advantage depends on the arm, or the moment arm. So what we want to do is we want to find the biggest R for the same amount of force, and that will give me the biggest advantage. So you can see this is like what, more than 3 times, a little bit over half, or a little bit over double of force applied here. And so that's what we're going to refer as torque. And we use the symbol tau for torque. The units on this thing, once we get it, are going to be Newton meters. And that's the way we write it. You may recognize Newton meters because 1 Newton meter is 1 joule, because that's force over distance. However, torque is not energy, and so we don't talk about joules with torque. We report it in Newton meters. Okay, so how can we actually calculate this? Well, there's a couple cases. One would be is if my force is perpendicular to the r vector being the distance from the axis, from the point. So in this case, since it's perpendicular to, the torque is just going to be the force times the distance. Pretty straightforward. All right, let's think if it's parallel. So if the force is parallel, that means it's either in the same direction as the position, or it could come this way. If you think about turning a door, so if you got on the edge of the door and you pulled out from the axis, it has 0 effect. So any force which is parallel to the r vector, the torque will be equal to 0. So perpendicular, we just multiply the force by the distance from the axis. And then parallel is always 0. And we're going to combine these now to figure out, well, what about at an angle? So if a force is at an angle, and this theta, it doesn't matter which way you measure it, this way, or you could extend this arm out like this and measure theta there. And that's the way I typically do it. It doesn't matter because they're complementary, so you get the same values for what we're about to do. So if I do that and I break up this force vector into its components, then you can see I get a perpendicular force, which we can call force tangent, and then I get a radial force, force rad. And you can see force rad is parallel. So the torque from this one equals 0. So this doesn't do anything to it. It's only this one that does something. So, and if we rewrite that in terms of the force, that's opposite. So we would get the force times sine theta. And then we know that the torque perpendicular is going to be, I don't know if I did F or R first, force times R, and in this case the only one that's acting perpendicular is this quantity here, and so we get torque is, let me take that off, the torque is going to be F sine theta times R. What I want to do is I'm going to rearrange this real quick because we're going to define something new. So R times F times sine theta. And this is going to be our definition of torque. However, this quantity here has a special name. This is magnitude, by the way. So if we want to actually deal with vectors, we need to convert this into a cross product. So that's R cross F. And these are vectors. And this is our definition of torque. So our definition of torque is that it's R cross F. We cross the vectors and we get a new vector called torque. To calculate it, you just go back to this. And you'll see that for the angle there, we can recover the previous two that we said. Because if we go to 90 degrees, so if the force were directly out this way, well, sine 90 is 0. So this whole thing goes to 0. And then if we're at 90 degrees, so it's perpendicular, sine 90 is 1. So we just get radius, the distance times the force. And so this is our general equation for torque. And this is the definition for the cross product. I was going to show you, so on your equation sheet, on the side that has all of the, you know what, let me just open it real quick. Okay, so here's your equation sheet. I'm just going to scroll down. The first thing will be this right here. There's your definition of torque. And then if you go to the back page where it has all of your general equations, down here at the bottom, your vector product. So we've already done the dot product before, which used cosine. Now we're doing the cross product, which would be sine. So we cross two vectors, we take their magnitude, and there you go. So what is a cross product? So a cross product is, it's when we want to multiply two vectors and our result is a new vector. However, the direction is not within the plane. So for instance, since in this case right here, force and the R vector are in the XY plane, then my torque vector is actually going to be in the Z plane. And this is where we'll go back to the right-hand rule. I have two pictures here. These are both the right-hand rule. This one clearly shows the cross product. So if you take A cross B, then the result is your thumb pointed up. And this one is the one you've worked with before. So if we curl our fingers in the direction of B, then our thumb gives us the direction of A cross B. So let's look at this. Let's think about what this means. Try to figure out the direction of the torque. So if you might want to use this one, I guess. It's hard to show on this. I'll show you in class. But for this one, since the force is going to cause a rotation in this direction, then you would curl your fingers. You place your palm facing up with your index fingers going this way. So along the R direction, that's the direction of your fingers, and then you would curl them up. And so your thumb would point this way out of the page. And so our torque here is actually going to come right along here. And that's in R. That would be my torque vector. And we would say it's out of the page. X and Y are the page, and Z goes this way, goes out of the page, this way goes into the page. We can signify that by a circle. So this means out of the page. And if we do an X or an X in a circle, either one, that means into the page. So, or you can try to draw a 3D like this, but so we come out, we cross it with F, and it comes out of the page. Conversely, so this would be a positive torque. I think we've learned about that before with circular motion. So if you did the right hand, this one, the right hand rule going around this way, that's positive. So we would move in the positive direction. Conversely, if I go R cross F, I'd have to turn my hand such that my finger points into the page. So my torque is going to be this direction. So if I were taking a screw out, I need to turn it this way to produce this torque out. And if I want to screw a screw in, I need to go the opposite direction to push it in. Either one of these, the way that this one works is your index finger is your R. Let me put that on there. So this is the R vector, and this is the force vector. So you just align your index finger along the R and then your middle finger along the F, and then your thumb would be the torque. For this one, you'd have to flip your hand upside, like, I don't know. You just got to align your hand right. It just takes some practice. Okay, that's torque. So why don't we work through some examples? Yeah, what I recommend, I'll put a couple up, and then you try it, pause it, and try them, and then I'll do them real quick. Okay, here's 4 problems. Let me explain how I drew this thing out. So we have a rod that's going to rotate about this point, O. And we want to calculate the magnitude and the direction of the torque at all 4 of these, F1, F2, 3, and 4. All the forces are the same, so we'll just say it's 10 newtons all the way across. The length of the entire rod is 1.5 meters. And then the R's are given. So force 2 is applied in this direction at 1 meter. Force 3 at this location, which is at 0.75 meters and 20 degrees. And then force 4 at 100 degrees at 0.25. So determine all of these torques. Go ahead and pause it, give it a try, and then I'm going to do it. Okay, so number 1. So number 1 is force 1. So the force is applied perpendicular at the end of the rod. So the R here is going to be the 1.5. And then torque is going to be R cross F. And we get the cross product is R times F sine theta. Theta in this case is 90 degrees, and so this just becomes the radius times the force, or the distance times the force. I'll say radius, but know that it's the distance from the point that we're interested in. So it would be 1.5 times 10. 1.5 times 10, which is 15 Newton meters. And then since it's rotating counterclockwise, this would be out of the page. Now keep in mind, it's always perpendicular. You're not going to have an angle measured for the torque. So R is this way, force is that way, so torque comes perpendicular to that plane. Comes out this way. All right. Number 2. Number 2 is in this direction. It's perpendicular to R. R is this way, and R is 1.0. So we get that the torque is going to be R cross F, which is going to be RF sine theta. Theta again is 90 degrees, so we just get RF. So which would be 1.0 times 10. So we get 10 Newton meters. And then following the right-hand rule, this one, the torque is going to be into the page. Into page. Number 3. So again, torque is always R cross F. And so my torque in this case is going to be RF sine theta. And so my force is applied 20 degrees. This would be the extension of the R, so 20 degrees. So I get 0.75 times 10 times sine 20. Make sure your calculator's in degrees when you do this. And you get 2.56 Newton meters. And since it's rotating, this is going to cause a rotation counterclockwise, following the right-hand rule. This would be out of the page. Number 4, similarly, torque is going to be R cross F, which is RF sine theta, which is going to be 0.25 times 10 times sine 100. And note, you can do it either way. I could have done 80 degrees here. Doesn't matter. And that's going to be, let me calculate real quick, times 10 times sine 100. 2.46. And since this will cause a rotation this way, then it's going to be into the page. So into page. Okay. And I think I'll stop there. The other thing to know is, like, if you're changing the angle, it's reducing the amount of torque that you'll get at any given position. So if I started swinging this out, it would go from a maximum at the perpendicular to a minimum at the parallel, because that's 0. And anything in between, it would just be decreasing as I started lowering this angle. So that's torque.